So, then so what we so the idea behind showing this lemma was that we wanted to prove Valiant-Vazirani's theorem. So, let me state that theorem once again, but before stating that, let me just define this language, so that it will be little easier to state that theorem. So, we define this language USAT to be set of all formulas, Boolean formulas, let us say in CNF form, all Boolean formulas phi such that phi has exactly one satisfying assignment. Okay. So, now we can restate Valiant-Vazirani theorem in this context, that there exists a probabilistic polynomial time machine M such that given any Boolean formula phi, let us say over n variables, if phi is satisfiable, then the probability that M given phi belongs to USAT is greater than or equal to 1 over A10, and if phi is unsatisfiable, then the probability that M given phi so, I will make this a little bit more stronger, belongs to SAT is 0. So, it is not even satisfiable, the new formula that we construct. Okay. So, this is just a rephrasing of the theorem that we stated at the beginning of last class. So, what we said was that if phi is unsatisfiable, the new formula that we construct is not satisfiable, and if phi were to be satisfiable, then the new formula has a unique satisfying assignment with at least so much probability. Okay. So, how does this follow from the lemma that we have? Huh? Yeah, so basically the way we are defining this language USAT, so the way in which complexity theorists look at this language USAT is they think of this as a promise problem. Okay. So, it is not exactly a language, or it is not exactly a problem in the traditional sense, in the sense that every string which belongs to the language has this property, and every string which does not have the properties outside this language. Okay. It is not exactly that, it is basically you have this set, let us say Okay, so I will just defer this proof. So, we have this set let us say 0 1 star or 0 1 to the power n, and you divide this into two sets, okay, set of all sum y, and there is another disjoint set which I call n. Okay. So, now we say that an instance belong to U set if it belongs to the y partition, and it does not belong to U set if it belongs to the no partition. Okay. So, in this case our no will be set of unsatisfiable assignments, and y is the set of assignments with exactly one, y is the set of Boolean formulas with exactly one satisfying assignment. Okay. Because
here we have promised that the x will belong to y.
Exactly. So, here we have the promise that the input belongs to only the union of these two things, but clearly there can be other formulas which lie outside, which have, let us say, two satisfying assignments or things like that. Okay. So, that is why I stated this as belonging to SAT instead of U SAT. Okay. So, these are known as promise problems in complexity, but yeah. So, how do we prove this? So, the proof is not difficult. Basically what you do is you construct a formula xi as follows. So, you first randomly pick k from the following set 0 up to n minus 1, okay, and then randomly pick a1. So, how many do we need? K plus 2, right? a1 through a k plus 2 in 0 1 to the power n. So, you need k such vectors, and also you pick these bits b1 through b k plus 2. Okay. And construct the formula, let us call it xi, as follows. So, xi of x is defined as, it is the conjunction of the input formula phi x with the following clauses. So, the first clause is a1 dot x plus b1 is equal to 0. So, it is basically the same way as this hash function works. So, if you just look at this entire thing that we have here, this is nothing but saying that h of x is equal to 0 to the power k plus 2, right. You have, so I am just splitting that into these k plus 2 clauses, and you can always come up with Boolean expressions with AND, OR and NOT gates, which will be equivalent to these whatever these clause states. And then we can just apply the earlier lemma. So, the earlier lemma says that for some k, okay, such that the cardinality of t lies between 2 to the power k and 2 to the power k plus 1, the probability that the number of x's that gets hashed to the all 0 string is 1 is at least 1 over 8. Okay. So, therefore, the probability that xi of x is in u sat is equal to the probability that, yeah. So, I do not want to write this entire thing, but basically it is equal to that there exists a k such that this formula phi of x conjunction with this h of x equal to 0 to the power k plus 2. So, this belongs to u sat, okay. And if you just apply the union bound here, this is greater than 1 over 8 times 1 over n, because the probability that the correct k is chosen is 1 over n. Okay. So, one immediate corollary of this result is that if there exists a polynomial time machine M that given a Boolean formula phi with exactly one satisfying assignment, outputs it, then NP is equal to RP. So, we know that RP is contained in NP, but suppose if you have a deterministic polynomial time machine which does the following. Okay. So, suppose if the machine is given a formula phi which does not have this property, then we do not assume anything about the machine. Okay. So, it can do anything, but if it is given a formula which has this property that it has only one satisfying assignment, then the machine will output it. Okay. So, the proof is again simple. So, suppose if you have such a machine, what you do is, given a formula phi, what you do is, first you generate all these different xi's. Okay. So, you are So, the idea is that for all k, construct xi 1 up to or xi 0. So, we are taking k in 0 up to n minus 1. So, you construct these formulas xi 0 to xi n minus 1, and then you feed it to this polynomial time machine. Okay. So, we know from the earlier thing that there is one which has so one of these formulas have a unique satisfying assignment with high probability if the given formula phi were to be satisfiable. So, the polynomial time machine outputs that formula, and that will help us to check whether phi is satisfiable or not. Okay. Yeah, so the you can check the details, but so any questions?
Weekend's condition to there is just a polynomial time randomly RPOC, DPPOC, RPOC.
No, but then you are strengthening the hypothesis, right? You are assuming a more powerful machine. I am only saying that if there exists even a polynomial time machine which has less power.
No, I am weakening the hypothesis. If they exist, RPOC.
See, RP machine has more power than a polynomial time machine, right?
So this hypothesis will have weaker condition.
Huh?
If we see this if you say this is RPOC, then this hypothesis will have weaker condition.
If it is an RP machine, then it implies that it's so if we have this condition, then it implies that M is also an RP machine, basically which has 0 error. Right? Yeah. Yeah, you can say that also. But so if we have a RP machine, yeah, it will work. Okay. So any other questions? Okay. So let's look at some definitions. So we will look at some counting classes. So in more generally, we will look at what is known as counting complexity, and we will try to come up with an analogous theorem of Velian-Vazirani's theorem. Okay. So if phi is a Boolean formula, okay, define sharp phi to be equal to the number of satisfying assignments of phi, okay, and in the same way you can define this function sharp sat, okay, that given a formula phi, it outputs the number of satisfying assignments of that formula. Okay. So this is just a number, it is not outputting all the assignments, but just the cardinality of that set. So more generally we can define what is known as the class, so I just state this as a definition, sharp P, okay. So this is not again a usual complexity class, in the sense that this is not a class of languages per se, but it is a class of functions. Okay. So sharp P is the class of functions f from 0 1 star to natural numbers. Let me just rephrase this a little bit. So a function f is said to be in sharp P if there exists a polynomial time machine M and let us say a polynomial P such that for all x f of x is the cardinality of the set of all strings y having size p of the length of x such that m given x and y accepts. Okay. So, in other words, what is this class of functions? Let us say in terms of the language NP, it is the number of certificates. So, an equivalent way of looking at this definition is, so f belongs to sharp P if there exists an NP machine N such that for all x f of x is the number of certificates of n on x. Okay. So, if you simulate the machine n on x, f of x is the number of certificates. So, it can be 0 also, in particular when the string does not belong to the language of n, number of certificates is 0, okay, and that is the only time when it is 0. Okay. So, let me just state this result. So, this language or this function sharpsat, so this is complete for sharp P. Okay. And the proof of this is basically observing that the reduction, Cook's reduction that we saw earlier in this course is basically a reduction which preserves certificates. Okay. So, if you are given a language in NP and for every string the corresponding formula that you constructed, that was basically a reduction which preserved certificates. Okay. So, whatever certificates that machine had for that string, the corresponding Boolean formula will also have that same number of certificates. Okay. So, yeah, I will not again go into the details of that proof, but you can check it for yourself. So, I will just leave this as an exercise with the comment that Cook's reduction is, so the technical term for this property is that it is parsimonious. Okay. In other words, certificates are preserved. Okay. So, I think even in the book, if you look at chapter 17 section 3, there is a short proof of this result. I mean, again they do not give a proof, I mean they just argue that y is Cook's reduction parsimonious. Okay. So, you can look at the following section. But okay, so let me come back to where we are. So, similar to that sharp quantifier, we can also define another quantifier. So, this is known as parity. So, parity of phi is equal to 1 if the Boolean formula phi has an odd number of satisfying assignments, that is, this is odd and it is equal to 0 otherwise. Okay. And again using this quantifier, we get the language parity sat, which is set of all formulas phi such that parity phi is equal to 1. Okay. All those Boolean formulas which have an odd number of satisfying assignments. So, now as an immediate corollary of Vaillant-Vazirani's theorem, we get the following result, that there exists a probabilistic polynomial time machine M such that for all Boolean formulas phi, if phi is satisfiable, then the probability that M of phi belongs to parity sat is greater than 1 over A10, and if phi is not satisfiable, then the probability that M of phi is also not satisfiable has one probability. I mean, in the other words, if M of phi is satisfiable, has 0 probability. So, and this is again obviously true because if M of phi belongs to U sat, it means it has only one satisfying assignment, which clearly means that it belongs to parity sat as well, because it is odd. So, 1 is odd. So, that is the reason why this is true. Okay. But so yeah, so this is something which seems very obviously true, and the question is that why are we going in this direction? So, the reason we are going in this direction is because we want to amplify this probability. Okay. So, let us look at, so let us come back to Vaillant-Vazirani's theorem, and let us ask the same question here, that is it possible for us to amplify this probability that is given by Vaillant and Vazirani? Can we do any better than 1 over A10? In other words, suppose if a formula is satisfiable, can I construct some formula xi which belongs to U sat with a value that is greater than 1 over A10? Okay. So, again last class we saw this argument as to how the success probability of a RP machine can be amplified. Okay. It is basically by taking some number of trials and you take the OR of all those trials, right. I mean, if one of those trials gives a positive answer, you output a positive answer, okay. And then the probability that you do get a negative answer is 1 minus the product of all these things, which is very small. But what happens here? I mean, what happens if we try to simulate that same argument here? Right. So, this okay. So, let us say that this is the formula xi that we get. Okay. So, when I run this machine once, I get a formula xi. Okay. Now, suppose I want to amplify this probability and I run this machine a second time, okay. And let us say I get a formula xi 1. Okay. Now, suppose that one of those formulas were to be true and the other is false. Can I claim that or can I construct a formula from xi and xi 1 which belongs to USAT? Okay. So, that is something which is not known to be true. Okay. In other words, if you let us say you take some t trials of this machine M, you run this some t times and you get some t formulas xi 1 up to xi t, how can you combine these formulas such that if the original formula were satisfiable, the combination of all these t formulae gave you only one satisfying assignment. So, that is something which is I mean not known. Okay. In fact, so this it is an open problem whether any number that is better than 1 over 8n can be achieved for this theorem. Okay. So, that is an open question. So, can we do better than 1 over 8n? Okay. So, this is open in the context of the USAT version of Valiant and Vazirani. But as it turns out, ParitySAT is much more expressive. Okay. ParitySAT has much more power than USAT, and we can go ahead and amplify this probability to any number which is exponentially close to 1. Okay. So, that is what we want to show. Yeah. So, let us see why that is true. So, is it clear what we are trying to get here? Any questions? Okay. So, let us look at some properties of this quantifier parity. So, let phi and xi be two Boolean formulae over n and m variables respectively. Then what we can do is we can construct Boolean formulae, okay, whose which have the following property. So, the first thing is that there exist okay, let me not write it this way. If we look at the okay, so the number of satisfying assignments of phi taken as a product with the number of satisfying assignments of xi is equal to the number of satisfying assignments of another Boolean formula phi dot xi, okay, where we define this phi dot xi, okay, let us say over the set of variables x comma y as phi of x and psi of y. Okay. So, let us just see what we are saying here. So, suppose if you have two Boolean formulae phi and xi over the set of variables x and y. Okay. So, think of x and y as a vector of variables. Okay. So, I can just write that here. Where x has n variables and y has m variables. Then if we consider the formula phi dot psi over the set of variables which is a concatenation of all the variables in x and y, defined as the conjunction of these two formulae, then the total number of satisfying assignments of this new formula is a product of the number of satisfying assignments of these two individual formula. Okay. And so, this is easy to see because you take any satisfying assignment of phi and you take any satisfying assignment of psi and you just concatenate those two, that will give you a satisfying assignment of phi dot psi. Okay. And similarly, you take any satisfying assignment of phi dot xi and you just look at the appropriate partition. So, the individual bit strings will be satisfying assignments of these two individual formulae. So, also we can do a similar thing if we want the sum of the two. So, suppose I want to define a formula, okay, let me call it. So, such that the number of satisfying assignments of phi plus the number of satisfying assignments of xi is equal to the number of satisfying assignments of this new formula, which we denote as phi plus xi. Such that yeah, so this is what we want. So, how do we define this? So, will or work, or will actually give much more. So, actually it will be right. So, it will have some m times 2 to the power n plus n times 2 to the power n. Okay. So, what you want is just this plus this, you want much lesser. So, or will not work. So, the way you can do it is there is a little tricky way to define this. Okay. So, before we go into this plus thing, how many variables does this new formula have in terms of phi and xi? Right. So, the number of variables of phi dot xi is m plus n, right. Okay. So, let us come here. So, phi plus xi, okay. So, we define a new set of variables z, okay, as equal to okay. So, let us assume that m is less than n. So, it is the formula z naught equal to 0 and phi of z 1 up to z n or the clause z naught equal to 1 and z m plus 1 is equal to 0 so on up to z n is equal to 0 and xi of z 1 up to z m. Okay. So, let us take a moment here and understand what is happening. So, we construct this formula phi plus xi. So, in this case it is a formula over n plus 1 variables. Okay. So, because we assumed that n is greater than m, but in general basically the number of variables in phi plus xi would be the max of n comma m plus 1. Okay. So, here since we are assuming n is the larger number, we have z as a over n variables.
So is it Zm plus 1 equal to 0 and Zm plus 2 so on up till?
Yes. So, z m plus 1 and z m plus 2 and so on up to z n, okay, because m is smaller than n, that is why. Okay. So, exactly what is happening here? So, let us understand the intuition behind this construction. So, what we want is that only if one of the, so let us look at the two clauses that we have. So, this is one clause and this is the other clause. Okay. So, one property of this entire construction is that both these clauses cannot be true at the same time, okay, because one contains z naught equals 0 and the other contains z naught equals 1. So, only one of them can be true. Moreover, let us say the first clause is true, then it implies that phi is also true, it has a satisfying assignment, and if the second clause is true, then it implies that xi is equal to true. Okay. So, if we take a satisfying assignment of phi, that we can translate into a satisfying assignment of phi plus xi just by setting z naught equal to 0, and if we take a satisfying assignment of xi, we can translate that into a satisfying assignment of phi plus xi again by setting z naught equal to 1, z m plus 1 equal to 0, so on up to z n equal to 0 and whatever is the value that is therefore z 1 to z m. So, note that these variables are exclusive. So, z naught only appears once here and then we have z 1 to z n, and here again z 1 to z m does not appear in any of these equalities. Okay. So, that is one direction. Similarly, we can also look at the other direction, that if phi plus xi has a satisfying assignment, okay, as we argued earlier that both these clauses simultaneously cannot be true. So, if this has a satisfying assignment, then either z naught equal to 0 or z naught equals 1. So, if z naught equals 0, then it means that there is a satisfying assignment of phi as well, okay, and if z naught equals 1, it means that these clauses have I mean these variables z m plus 1 through z n all have a value 0, and there is a satisfying assignment for xi as well. So, you can see both directions. Okay. So, that is the essential idea, but I will just leave it as an exercise to formally prove this. Okay. So, just go back and write out the proof. So, is this construction clear? Okay. So, now let me just state one more property and then we will leave it at that point. I will state this as an observation. So, firstly, if you look at parity of phi and parity of xi, so this is equal to parity of the formula phi dot xi. So, in other words, if so, when is the left side true, or when does the left side evaluate to 1? When both these are odd, when both these have an odd number of satisfying assignments. So, if both these have an odd number of satisfying assignment, the product of two odd numbers is odd, which means that this is also true. And similarly, the only way in which the product of two numbers can be odd is if both the numbers are odd, which implies that this is also true and this is also true. Okay. So, that is easy to see. The second property is that, so basically what we are showing here is that this parity operation is, or this parity quantifier is closed under the Boolean AND operation. Similarly, it is also closed under the NOT operation. So, NOT of parity of phi is equal to parity of the following formula. So, I will call it phi plus 1, where phi plus 1 is some formula such that number of satisfying assignments of phi plus 1 is equal to number of satisfying assignments of phi plus 1. Okay. So, in other words, you can take this formula to be xi, where it is some trivial formula, let us say x, it has only one variable. If it has only one variable, then it has exactly one satisfying assignment, which is 1. So, you can trivially construct a formula by applying this construction. Okay. So, now so why is this true? Because if this were to be true, then now this becomes odd, even, which makes this false, and vice versa. Okay. The third one is a little bit tricky, but again not difficult to see, is with respect to the OR operation. So, phi parity phi or parity xi is equal to, again parity of a single formula. So, what do you think it should be? So, we want this to be true if at least one of them is true. Yeah, so yeah, you can use the NOT also by using De Morgan's law, but you can give a more direct formula. So, it is phi plus 1 product, it is phi plus 1 dot xi plus 1 plus 1. Okay. So, if one of them is true, so let us say this is true, okay, that means this has an odd number. So, then this will have an even number. So, an even number product with any number is always even. So, this entire thing becomes odd, and the only way this will become even is when both these numbers are odd, which is when both these have an even number of satisfying assignment, which means that both these are false. Okay, so that is what I had. So, now actually you can see yourself that you can try to see how this will help you to boost this probability, but anyway we will discuss it next time, how these things can be used. Okay, so anyway we have overshot, we will stop here.